Hi, and welcome back to the next lesson in the video series. Today we'll be discussing vertical motion under the influence of gravity, and in particular, vertical projectiles. That's when you throw something into the air, it'll reach its high point, slow down and stop, and then eventually it will turn around and free fall. But since we covered free fall in the last video, now we will cover vertical projectiles. As we did in the last video, let us set up the initial conditions for a vertical projectile. The diagram is very similar, except this time the ball starts from the ground and goes into the air, working against gravity. The ball is launched, say, from your hand if you throw it straight up in the air, with a launch speed of v0. When the ball ascends to the height, its y max, slows, moving against gravity until it comes to a final speed of 0. It hovers there for a millisecond or so, and then it begins to free fall. Of course, the time it takes to rise is also equal to the time it takes to fall. Let's take a look at how equations 3, 4, and 5 are modified to accommodate a vertical projectile scenario. Starting with equation 3, Vf equals Vo plus At, we realize that the only modification would be that gravity replaces the acceleration, and you must use a negative sign. Let me interpret this for you. This says that the speed of the object at any time since it was launched, that is what the v final y is, equals the initial launch speed minus the speed that it loses from decelerating or accelerating against gravity. An object thrown into the air does not get faster and faster, which is what a plus sign would imply, but gets slower and slower as it moves against gravity. We know that at the top of the flight path, the final speed, Vfy, would be equal to 0. Putting a 0 in for v final y and subtracting over this initial speed cancels negatives and allows us to solve for the rise time, which is Voy over g. This is an incredibly important conclusion, and this result will be used especially in the next unit when we discuss two-dimensional motion. So the rise time is equal to Voy, the initial vertical speed, divided by gravity. We also call this T up, time up. Here we have the distance or displacement formula in the vertical direction, d being replaced by y. The initial speed, v0, is Voy. That's the vertical launch speed minus the effect of gravity on that object. So as an object rises, it slows down, as we know from the previous equation, and in slowing, decelerating, it does not cover as much distance for each second, so it doesn't rise as far as it did in the second prior. That's because when you work against gravity and you get slower and slower, you eventually come to a full stop. The height above the ground after it's launched is equal to the launch speed duration minus the deceleration duration. And we're going to graph this out soon and you're going to see. And here we have finally formula 5. V final squared equals Vo squared plus 2AD. We applied the initial conditions that the final speed at the top of the ascent is 0 and acceleration is negative gravity. When we subtract this initial speed over, we cancel out the negatives and we get this important relationship, Voy squared equals 2g. If we took the square root of this, we could then determine that the initial speed of the object equals the square root times 2 times height. If we knew the height, we could determine what initial speed it was, or we can determine how high it will go based on an initial velocity, and that's what we have here. By dividing 2g under the Voy squared, we have the y max formula. The maximum height for a given launch speed is equal to the square of the vertical launch speed divided by double gravity. Let's take a look at an example. Let's try this problem. A rock is thrown vertically upward with an initial speed of 50 meters per second, neglecting friction. Based on the information provided, answer the questions below and show all work, formula, solution, and answer. First question is, how high will the rock ascend? Well, we know from formula 5 that we could solve for y, knowing that the initial speed is 50 meters per second. The final speed at the top of the ascent is 0 meters per second. Solving for y max, we get Voy squared over 2g. Plugging that in, we get 127.55 meters. That's how high the rock will ascend. The second question asks, what is the time to reach Y max? Meaning, how long does it take to get to the high point? And the answer is simple. We take Formula 3 and we solve it for t. Since the final speed at the top of the ascent is 0, this formula simplifies to t equals launch speed divided by gravity, which gives us 5.1 seconds. In the third question, we're asked, how long is the rock in the air until it strikes the ground again? That's the total time of flight. And in the case where there is no friction, the time up plus the time down, which are the same, add up to equal the full time of flight. So we take the rise time and we double it. We get 10.2 seconds. In question number 4, we're asked, what is the impact speed of the rock as it strikes the ground at the same level as it was launched? Well, we take Formula 5, the v-squared formula, we solve it for v final. This is simply a freefall problem, and now we know that the initial speed of freefall is 0, so the final speed from equation 5 is what we're looking for, which is equal to the square root of 2 times gravity times the height from which it fell. And that gives us 50 meters per second, which matches the launch speed of 50 meters per second. Here in question 5, the rock is thrown upward on the moon, which has a significantly less gravity, g equaling 1.6 meters per second squared instead of the Earth's 9.8 meters per second squared. We're going to use the same launch speed of 50 meters per second. What's the new maximum height of ascension? It's the exact same question as number 1. The only difference is we're going to replace gravity of the Earth with gravity of the moon. So we still use Formula 5. We know that the speed at the top is 0 and the initial speed is 50. V squared over 2g, but this time g is 1.6, and so we get 781.25 meters. Here is the data chart for an object vertically projected at 50 meters per second. We can see that the object slows from a speed of 50 all the way down to 0, and it goes from a height of 0, the launch position, all the way to a height of 127.5. Let's take a look at the graphs for this. Here is the graph of d versus t for upward deceleration. When you throw an object into the air, it slows as it climbs to its ascent. The t is on the x-axis, the d is on the y-axis, and you can see that this curve is half the parabola, and it is a slope that is decreasing until it is flat at this spot right here, which means that it slowed and slowed until it stopped. The equation is y equals minus 4.9 t squared plus 50t. The 50 is the v0, and the 4.9 is the 1/2 of acceleration. Let's take a look at the vt graph for the same motion. Here is the equivalent vt graph for upward deceleration. When an object leaves your hand and it ascends, it fights against gravity and decelerates, therefore it gets slower. It has an initial speed of 50 meters per second, and it loses 9.8 meters per second for every second that it travels. So the original 50 loses 9.8 per second, and this is why you have a constant negative slope VT graph. Let's take a look at both of these together. And in conclusion, we can see the DT and the VT graphs for upward deceleration of an object that is vertically projected. Here we have the initial time from 0 to 5.1 seconds to rise time. We have an initial speed of 50 from the lowest level, or the ground, or the hand in this case. And as it rises, it slows, decelerates to 0. And as it goes from the ground, it goes up in the air to about 128 meters. We can see the two formulas here represent the shape of deceleration. This is the forward deceleration shape, which you should recall from the last video. And this is a deceleration VT shape, which you should recall. That is the pair. These two go together all the time. This negative parabola, this decreasing tangent on this parabola, goes with this negative slope for VT. And there you have it. I hope you enjoyed this lesson, and thank you for watching. We'll see you in the next video.